Hello everyone. Welcome to the demonstration video of the ISRO Robotics Challenge 2026. My name is Roshan Raj and I am from the branch of Computer Science and Engineering, the captain of team Adi Shakti, representing BIT Sindri. Besides me is JATAYU, our autonomous UAV designed for the Ascent Swarm Expedition mission. When we started this project, we knew that the real challenge was not just building a drone that could fly, but to design a system that is independent and is capable to survive in a GPS denied environment. We have built a robust, fully integrated surveyor, and we are incredibly excited to walk you through our engineering journey. So let's get started. So over the next few minutes, you are going to see how different specialized subsystems come together in order to execute a drift-free navigation.
Meet JATAYU, named after the mythological guardian known for his air vigilance. JATAYU uses X configuration carbon fiber frame, which has overall dimension of 0.61 meter by 0.61 meter and an elevation of 0.61 meter from the ground. JATAYU is under 2 kg weight constraint with the overall takeoff weight of 1.61 kg, which required a operating power of 329 watt, which is given by a 4S LiPo battery, and which due to this power system, the JATAYU is capable of a flight time of 0.336 hour per charge. To generate the sufficient lift, JATAYU uses 4 10-inch carbon fiber propeller which generate a lift of 32 Newton, which gives a thrust to weight ratio of 1.76. Due to this system, JATAYU is capable of stable hover, vertical takeoff and precise landing without tipping.
Hello everyone, myself Harshanjit from the Department of Electrical Engineering. Currently, I am a second year undergraduate and I am giving you an overview of our hardware system. So let's dive into a hardware system that powers JATAYU. The central brain of our micro UAV is the Raspberry Pi 5 equipped with 8 GB of RAM and paired with Raspberry Pi AI hat. This combination provides computational power required to process complex odometry and AI-driven feature detection smoothly at the edge. For precise dynamics, we rely on PIXOC's 6C flight controller, which act as our reflex system to handle stabilization, integrated sensors data, and execute trajectory commands. Our primary eyes consist of Intel RealSense camera for depth mapping and RGB capture supplemented by a downward-facing PX4 optical flow sensor for zero drift velocity holding during hovering. To translate these computational into physical movements, we required 4 T-motors driven by high-performance ESC. Powering all these components is a 4S LiPo battery managed by a power distribution board, ensuring a stable and regulated voltage supply to all the critical electronics throughout the mission.
Hi everyone, I am Omnath Mandal, a third year chemical engineering student, and today I am exploring software subsystem. The intelligence of JATAYU is powered by ROS2 JADI framework, which manages real-time messaging across our entire sensor and processing suite. At the core of the system, Python handles high-level mission logic and computer vision, while MAVSDK bridges this script to the PIXOC flight controller via the MAVLink protocol for precise autonomous control. To ensure reliability, we utilize Missile Planner for telemetry and Gazebo Harmonic for high-fidelity physics simulation before our algorithms testing our algorithms in a digital world before any hardware leaves the ground.
Hi everyone, this is Shivangi from Chemical Engineering Department. Welcome to the most critical aspect of JATAYU's autonomy, navigating without GPS. In planetary exploration, satellite navigation simply isn't an option. To solve this, JATAYU relies entirely on a custom visual inertial odometry pipeline powered by ORB SLAM3 algorithm. Here is how it works. As the drone flies, the front-facing camera streams continuous stereo depth data and high-speed inertial measurements directly to the Raspberry Pi 5. The ORB SLAM3 algorithm acts as the drone's visual cortex, constantly extracting thousands of key points from the terrain below, like rock edges and surface texture. By tracking how these features move from frame to frame and fusing that with IMU acceleration data, the system calculates the drone's exact position, orientation, and the velocity in 3D space. This continuous loop allows JATAYU to dynamically build a local map of its surroundings, avoid obstacles, and execute precise, drift-free search patterns completely independent of any external navigation. Free search patterns completely independent of any external navigation aids.
Hi everyone, I am MD Kaf Nizami from Department of Electronics and Communication, currently in a second year. I am explaining our autonomous drone docking system. The main goal is to automate the charging system. When a drone lands, the docking station center it perfectly. We have placed a matching contact sheet. When they touch, the charging starts automatically. For the power, we are using a 4S LiPo battery. I have optimized it by making the ground common by both XT60 and a balance lead. This reduces the setup to just 6 pins, both charging and self-balancing at once. It's simply a robust way to keep drone flying without manual battery swapping.
Hi everyone, myself Sardhanand Kumar from the Department of Chemical Engineering. I am going to explain about the data transfer of our drone JATAYU. After completing its task, the drone JATAYU lands safely and starts transferring data to the base station. The onboard Raspberry Pi automatically connects to the base station using high-speed Wi-Fi and it establishes a secure connection. For data transfer, we use ArcSync, which is very efficient method. And remember this thing, it does not send the entire file again if the connection is lost. Instead, it resumes from where it stops and only transfers the remaining data. It ensures fast, reliable, and secure transfer of important data like images and detection results without any loss.
Hi everyone, this is Aditya Raj from Mechanical Engineering Department, and today we are talking about JATAYU. Before taking off, JATAYU receives a few reference photos of its target like specific rock formations. While flying, the drone's onboard computer constantly compares its live camera feed to those original images. If it is at least 85% sure it finds a match, it stops, logs its exact location, and takes a high quality picture. After it returns to base, the main computer double checks the new photograph against the original. And if everything aligns, the mission is officially a success. Thank you.
Hi everyone, myself Saurav Divakar from Chemical Engineering branch. Welcome to the final and most step of JATAYU's flight, landing. For charging our drone, must land very accurately. Even a small error of a few centimeters causes misalignment between the copper pads and charging pins. To solve this problem without using GPS, we use something called Aruko marker. Here is how it works. At the center of the base station, we place a special black and white Aruko marker. When JATAYU comes back to its home area, it uses its camera to look for its marker on the ground. Once the Pi detects the marker, it calculates the drone exact position and angle. Then JATAYU automatically makes a small adjustment to correct its position. It aligns perfectly above the marker and slowly lands straight down. This process ensures that charging pads connect properly every time, giving a smooth and accurate landing.
Hello everyone, this is Adil Manawar, a second year undergrad student of Electronics and Communication Engineering. Operating on other planet without GPS is a huge task. So we have built JATAYU to handle all what ifs entirely on its own. Think of it like a survival instinct of a robot. Our two main computers, Raspberry Pi and Pixhawk, continuously communicate with each other. If that communication drops, Pixhawk realizes it immediately, and instead of crashing or drifting away, it immediately switches to its ground sensor so that it can lock on the ground while hovering in a place and trying to reboot its system. If the system can't get recovered or the battery gets dangerously low, JATAYU doesn't take risk. It immediately cancels the mission and does a soft control landing while protecting its hardware and the data we have collected. And in case of emergency, if the motor fails, the drone gets drifted or disoriented completely, it can trigger an emergency kill switch that stops the prop and minimize the impact. So whether it's a software glitch or low battery, JATAYU is all programmed to protect itself first, so we can always recover it and fly all over again.